Good day to everyone. Today I am going to discuss RLC Series Circuit, where a resistor, an inductor, and a capacitor connected in series with AC voltage supply. Supply voltage is Vs, and the current flow is shown as I. Vs here is the RMS value, where the actual voltage values are always changing, relevant to its sinusoidal waveform positions. Vr, Vl, and Vc are the voltage drops across the resistor, inductor and the capacitor respectively. R, L, and C are the resistance measured in ohms, inductance measured in Henry, and the capacitance measured in farads. First we see the behavior of the resistor on the circuit. Here, the current and the voltage waveforms are moving on the same phase, starting together from zero value. Both curves reach the maximum and the minimum values also at the same time. If you see this on the phasor diagram, it looks like this, and the values for the current and the voltage are positive, from 0 degrees to 180 degrees. Likewise, from 180 degrees to 360 degrees, values are on the negative side. Rate of change of angle on the sine waves is given as angular velocity denoted by omega. Omega is equal to 2 phi multiplied by f. 2 phi is the full circle of 360 degrees, converted to radians. F is frequency of the supplied voltage measured in hertz. This equation is required when calculating inductance and capacitance later here. Let's take current and the voltage onto a graph, where both are on the same direction on the horizontal x-axis. Let's go to the inductor now. The blue-colored current wave started from 0 when the voltage sine wave has reached its maximum value. Here on the phasor diagram too, you can see the voltage sine wave is ready to start a new sine wave from 0, but the current sine wave is still on the previous cycle, needing another 90 degrees to move before starting a new waveform. Current and voltage sine waves are out of phase by 90 degrees and current lags behind the voltage curve by 90 degrees. Move both current and voltage by another 90 degrees, and we can arrange current on the horizontal x-axis on the graph, and the voltage line VL acts on the y-axis vertically upwards. Then on the capacitor, current wave has already started and gone to its maximum value, when voltage waveform is about to start from 0 value. This is clearer on the phasor diagram. Current waveform has started 90 degrees earlier from 0, and achieved its maximum value also, when voltage curve starts from 0. Current and voltage waveforms are out of phase by 90 degrees here also, but current is leading by 90 degrees in front of voltage. After reversing this by 90 degrees, we can get current onto the horizontal x-axis on the graph, and the related voltage Vc acts downwards on the y-axis. When you take all three graphs onto the same vector diagram, directions of the voltages looks like this, related to the direction of the current. Let's go back to the resistor again. Resistor always acts against the current flow in an electrical circuit. The value of the resistor is given in ohms and is referred as resistance R. By increasing the resistance on a circuit, you can reduce the current flow through it. Voltage across a pure resistor is always on the same phase with its current flow. Let's consider an inductor now. Inductor 2 acts against the current flow through it, and this resistivity depends on its inductance L, measured in Henry, and the related inductive reactance XL, measured in ohms. Inductance of a coil is directly proportional to its inductive reactance. If inductance is increased, inductive reactance also goes up. Current waveform through a pure inductor always lags 90 degrees behind its voltage waveform. Next we go to the capacitor. Capacitor also resists against the current flow on its circuit. Capacitance C of a capacitor is measured in farads, and the related capacitive reactance XC is measured in ohms. Capacitance of a capacitor is inversely proportional to its capacitive reactance. If capacitance is increased, capacitive reactance will decrease. Current waveform through a pure capacitor always leads 90 degrees in front of its voltage waveform. Now, let's assume 3 voltage drops across the resistor, inductor and capacitor are 175, 300 and 150 volts respectively. Supply voltage is not given here. Although the voltage drops are acting on different directions, we can find the vector sum or the supply voltage here by adding these 3 together on a vector diagram. Current line is also drawn here, but not compulsory since the magnitude is not known. Since the VL value of 300 is the largest along the y-axis, we draw it first proportionately on the graph. Then, starting from the endpoint of it, we draw VR at 175 horizontally. VC at 150 should be drawn downwards from there, since direction of VC is vertically downwards. Then, draw a straight line from the start point of first line to the end point of the last line to get the vector sum of the 3 voltages, Vs. If these lines are drawn proportionately, according to a scale, supply voltage can be taken by measuring the length of the resultant line. Further, we can solve this little differently also. First, draw the VR value horizontally to the right. Then the difference between 2 vertical values need to be drawn vertically upwards or downwards accordingly. Here also, the resultant line is the supply voltage denoted by Vs. Angle shown on the right-angled triangle shows the direction of the supply voltage related to VR, VL, and VC. This triangle is called the voltage triangle. Since we know 2 values of the 3 sides on this right-angled triangle, we can use Pythagoras' theorem to find the third side, which is hypotenuse. So we get 230.5 volts for Vs, or the supply voltage. Let's assume that the current flow is 3 amperes on this circuit. Then we can use Ohm's law to find the resistance R and get 58.3 ohms for that. Same way, for inductive reactance, XL, we get 100 ohms. Further, for the capacitive reactance, XC of the capacitor, answer is 50 ohms. These 3 values resist the current flow on this circuit, and as a whole to call this resistance, we use the word impedance. Total impedance of this circuit can be found out by using Ohm's law. Just divide the supply voltage of 230.5 by current flow of 3 amperes, and you get 76.8 ohms for total impedance, Z. Total impedance also can be found out in a different way. On the voltage triangle, using Ohm's law, replace VR, VL minus VC, and Vs, with IR, IXL minus IXC, and IZ, respectively. Now, the ratio between the sides of the right-angled triangle can be given as Vs2, VR2, VL minus VC. It also can be written as IZ2, IR2, I into XL minus XC. Since all 3 has I on it, we can omit that by dividing all 3 with I. So, you get final ratio as Z2, R2, XL minus XC. Now, the voltage values can be replaced with the new values of R, XL minus XC, and Z. This is called impedance triangle, and the total impedance can be found out using Pythagoras' theorem. After substituting the values on the equation, you get 76.8 ohms for the total impedance of this circuit. This is the same value we found previously using Ohm's law. Now we need to find out inductance, L, and capacitance, C. For this, you need to recall the equation for angular velocity, that is omega equals 2 phi, multiplied by f. Let's assume the value of frequency as 50 Hz. To find out inductance value, equation is inductive reactance equals omega multiplied by L. First, substitute the angular velocity or omega with 2 phi f, since we know these values. Now, rearrange the equation to make inductance the subject. Then, inductance equals inductive reactance divided by 2 phi f. After solving the equation, you get 0.318 Henry as the inductance value of this inductor. For easy reference, we can present this inductance value as 318 millihenry. To find out capacitance value, equation is capacitive reactance equals 1 over omega multiplied by C. First, substitute omega with 2 phi f. Rearrange the equation to make capacitance the subject. Then, capacitance equals 1 over 2 phi f multiplied by capacitive reactance. After solving, you get 0.0000637 farads as the capacitance value of this capacitor. For easy reference, this value can be given as 63.7 microfarads. Hope you got fair idea now of a circuit where a resistor, an inductor and a capacitor connected in series. If this video is helpful, please subscribe to the channel. Thank you.